Assalamualaikum warahmatullahi wabarakatuh. We are from Group 1. Today we're going to present you about the major losses in pipe. Our group member consists of Nabin Raj, Arif Imran, and me, Muhammad Fazli Fitri. So, the abstract of in this experiment are: number 1. The total energy loss in a pipe system is the sum of the major and minor losses. Major losses are associated with frictional energy loss that is caused by the viscous effect of the fluid and roughness of the pipe wall. Number 2. Major losses create a pressure drop along the pipe since the pressure must work to overcome the frictional resistance. Number 3. In this equation, the friction factor F, a dimensionless quantity, is used to describe the friction loss in the pipe. In laminar flow, F is only a function of the Reynolds number and is independent of the surface roughness of the pipe. And the last one, in the fully tubular flow, F depends on both the Reynolds number and relative roughness of the pipe wall. By solving problem, F is determined by using the Moody diagram.
Good evening. Now I'm going to explain the objective. Our first objective is determine pipe friction factors, which are also known as resistance coefficient. What is pipe friction factors? Pipe friction factors are loss in pressure of a fluid due to the interaction between the fluid and the pipe. Next is introduction. As we know, there are two types of losses. One is major loss, another one is minor loss. Major losses and minor losses predominant in fluid flow through a pipe network. Major losses are associated with the frictional energy loss that is caused by the viscous effect of a medium and a roughness of the pipe wall. Minor losses are due to the pipe fitting, changes in flow direction and changes in flow area. Basically, for major losses is due to the friction caused by the fluid and the pipe wall. If we use a pipe wall with higher roughness, then we have more losses. As we go to minor losses, is due to the piping fitting. If we use a smaller pipe, then the fluid flows from the smaller pipe to the bigger pipe. We can see the losses. Due to the complexity of the piping system and the number of fittings that are used, the head loss coefficient is empirically derived as quick means of calculating the minor head losses. The Darcy equation is the most widely accepted formula for determining the energy loss in pipe flow. In this equation, the friction factor, a dimensional quantity, is used to describe the friction loss in a pipe. In laminar flows, friction factor is only a function of Reynolds number and is independent of surface roughness of a pipe. In fully turbulent flows, friction factor depends on the both Reynolds number relative roughness of the pipe. Friction factor is determined by using the Moody's diagram. The Reynolds number can be calculated using the data of internal diameter, velocity, kinematic viscosity of flowing medium, and it's as follows. This is the formula to find the Reynolds number. As you can see here, kinematic viscosity of flowing medium. What is, first of all, we have to know what is viscosity. Viscosity is the measure of fluid propensity of the flow. And what is kinematic viscosity? Kinematic viscosity is the ratio between the dynamic viscosity and the density of the fluid. Different temperature will give us different kinematic viscosity. So it will affect the Reynolds number. The speed of the flowing medium can be calculated using the data of the internal pipe cross-sectional area, flow rate, and it is follows. This is the formula to find the velocity of the fluid. For turbulent flow in smooth pipes, the friction factor, the Borosius formula, valid for Reynolds number smaller than 10 power of 5 and can be calculated as follows. This is the formula to find the friction factor with the Reynolds number less than 10 power of 5. Meanwhile, for Colebrook's formula, the friction factor in turbulent flow can be calculated using this particular formula. Equation 6 is an implicant formula that must be iteratively resolved. First, estimates the value of friction factor, place it in the formula, and calculate the internal approximation. This approximation is reused in the equation to calculate a second approximation. If the estimated value is taken from the Moody chart, the internal approximation is generally sufficiently accurate and the value only different after the third decimal point. So this is basically the another formula to find the friction factor. Alternatively, the value of friction factor can be directly be obtained using the Moody's chart. That's all from me. Thank you. Okay, now I'm going to explain the theory. Generally, in turbulent pipe flow, the Reynolds number will be between 4 times 10 power 3 to 5 times 10 power 5 between 2 points for horizontal pipe with the constant internal diameter d with no minor head loss accounted, whereby the total head loss is equal to the major head loss because there's no minor head loss, the pressure loss, and the major head loss using the Bernoulli's equation. Basically, this is the formula to find the pressure of the liquid, and this is the formula to find the major head loss. Okay, P is denoted as pressure loss between 2 points where the height is same as we see here. Z1 is equal to Z2. L is the length of the pipe. D is denoted as internal diameter of the pipe. Then density of flowing medium. V square is square of the speed of flowing medium. G is gravity constant, and HL is the major head loss. For turbulent pipe flow, the pipe friction coefficient depends on the equivalent pipe roughness and Reynolds number. An example of equivalent roughness based on the type of pipe are listed in table 1. As you can see here, different type of pipes have different type of roughness, which causes them to have different friction coefficient. As you see that steel have more roughness, which means that they have more friction coefficient compared to plastic and glass, which the roughness is 0. So eventually they have the lowest friction coefficient. Moody's chart in figure 2 summarize the relationship between Reynolds number, friction factor, pipe roughness, and internal diameter. As you can see here, using this Moody's chart, we can find the Reynolds number, friction factor, and pipe roughness very easily.
So now I'm going to talk about the methodology. So the procedure, the apparatus for this experiment is 2-tube manometer, 6-tube manometer, differential pressure sensor, digital display for pressure, pump switch, main switch, electronic pressure sensor, return hose, return valve, interchangeable measuring object, water tank, drain valve, pump, various penetration feeding hose, gate valve, thermometer, rotameter, tube manometer. So the procedure for this experiment is, first, both the feeding and return hose were connected to the tested pipe section. Second, the manometer tubes at one of the two manometer was connected to the tested pipe section. Third, the main switch and pump was switched on. The gate valve was slowly opened until the reading of rotameter or actual flow rate reached to Fourth, the ventilation valve on top of the 2-tube manometer was opened by turning it to anti-clockwise direction to release all the bubbles in the system. If there is no bubble present, close the ventilation valve by turning it to clockwise direction. Fifth, the gate valve was closed and the pump was turned off. The ventilation valve on top of the 2-tube manometer was slowly opened until the preset minimum reading of 2-tube manometer reached 25 mm for galvanized steel and PVC pipe, while 1 mm for copper, PVC 20 and PVC 32 pipes. The gate valve was slowly opened until the level of water at 2 tube manometer of H1 reach the maximum while H2 at minimum. The 2 tube manometer reading H1 and H2 temperature and QH at rotameter were recorded. The QH was reduced to 5 different values by adjusting or reducing the opening of the gate valve. The minimum value of QH showed around 0.2. All the reading tube monitor were recorded. 7th, the manometer tubes at 2 tube manometer was transferred to differential pressure sensor. Prior to recording the reading differential pressure sensor for 5 different value of QH as in step maximum 2, minimum 0.2, ensure that there is no bubbles present in the system. This was opening the ventilation valve at different pressure sensor. If there is no bubbles present, close the ventilation valve and record the QH, temperature and the differential pressure reading. All the manometer tubes were removed from the system. The gate valve was closed and the pump was turned off before changing the feeding and hose was returned to another pipe section. Step 2 to step were repeated. After finishing, all the manometer tubes were removed from the system. The gate valve was closed and the pump and the main switch were turned off. So for the data for pipe galvanized temperature, this is the data for pipe galvanized temperature at 30 degree. As you can see, 0.6. The differential measure pressure M bar is 17.2, 0.5 is 64.2, 0.4 is 55.2, 0.3 is 45.1, and 0.2 is 35.9. For pipe copper, the flow meter at 1.5, the differential pressure is 59.8, 1.3 is 50.7, 1.1 is 44.1, 0.9 is 37.5, 0.7 is 32, 0.5 is 27.4, 0.3 is 23.4. And for the PVC pipe 60mm times 18mm, 0.7 is 76.1, 0.6 is 66.6, 0.5 is 57.2, 0.4 is 48.5, 0.3 is 40.8, 0.2 is 33.7. And for the PVC pipe 20mm times 1.5mm, 1.9 is 56, 1.3 is 46, 1 is 37, 0.7 is 29.6, 0.4 is 23.7. For PVC pipe 32 times 90mm, the flow meter at 2.7 is 24. The different pressure is to 24.3. At 2.2 is 22.2. 1.7 at 20.3 and 1.2 at 18.7 and 0.7 is at 17.4. So for the discussion, compare the coefficient of friction for each of the tested pipe in your experiment with using the coefficient of friction from Moody chart and calculation using formula of Blasius, Colebrook and Moody. Explain the possible reason for the difference in the value. So as you can see, for pipe galvanized at temperature 30, when we using the formula V, it is equal to 4Q over pi times internal diameter, we get 0.8762 meter per second. And to get the RE, V times internal diameter over V. And for the RE, we get 13,894.0442. For the Moody chart, we get the F is 0.042. By using the Blasius formula, 0.042 for Blasius formula 0.316 over root of RE, we get 0.029. For Colebrook formula, 1 over square root of F equal to negative 2 log over internal diameter over 3.7 plus 2.51 over RE times square root F, we get the F is 0.0439. And by using the Moody formula, F is equal to 0.001375, 1 plus 200 epsilon over internal diameter plus 10 to the power of 6 over RE to the power of 1 over 3. By using that formula, we get F equal to 0.005807. And for the pipe copper, the V, we get 1.243 meter second minus 1. And the RE, we get 25751.65. By using the Moody's chart, we get F is equal to 0.026. By using the Blasius formula, we get that F is equal to 0.0249. And by using Colebrook formula, we get F is equal to 0.0246. By using Moody formula, we get F is equal to 0.0047. For the PVC pipe 16mm times 18mm, V is equal to 0.551. And the RE is equal to 12716.62. And the Moody's chart for the PVC pipe 16mm times 18mm, F is equal to 0.029. And the Blasius formula, we get that F is equal to 0.0297. By using the Colebrook formula, we get that F is equal to 0.0292. And using Moody formula, we get F is equal to 0.0053. And for PVC pipe 20mm times 1.5mm, by using the calculation, we get the V is equal to 2.302 meter per second. RE is equal to 37656.557. And from the Moody's chart, we get F is equal to 0.024. And by using Blasius formula, we get F is equal to 0.0227. And by using Colebrook formula, we get F is equal to 0.226. And by using Moody formula, we get F is equal to 0.0042. Lastly, for the PVC pipe 32mm times 1.9, V is equal to 0.7557. And for the RE, we get 29214.8. And at the Moody's chart, we get F is equal to 0.023. By using the Blasius formula, we get F is equal to 0.24. And by using Colebrook formula, we get 0.0237. And by using Moody formula, we get F is equal to 0.0045. The difference is made due to the error when conducting the experiment. So the difference in value may also because Moody chart formula, it is stated that the accuracy may differ in pipe surface type. It is the same also for Colebrook formula, while Blasius formula, it is emphasized for both surface type. Rank the pipe in ascending trend based on their major head loss value obtained from your experiment. Briefly explain the factor influence your pipe ranking selection. Okay, by using the formula, head loss is equal to F times 1 to the power times V to the power squared over 2 times internal diameter times gravitational. We get that from galvanized pipe, we get for the head loss, we get 0.01294 meter. And for copper pipe, we get 0.123 meter. For PVC pipe, we get 0.0264 meter. PVC pipe 20mm times 1.5mm, we get 0.5228 meter. And lastly, for PVC pipe 32 millimeter times 1.9 millimeter, we get 0.0237 millimeter. So the rank for the pipe is the lowest is PVC pipe 32 millimeter times 1.9 millimeter. The second is PVC pipe 16 millimeter times 18 millimeter. The third is copper pipe. The fourth is galvanized steel pipe, and the biggest head loss is the PVC pipe 20 millimeter times 1.5 millimeter. This is because PVC pipe with the dimension of 32 millimeter times 1.9 millimeter has the largest inner diameter size, which is 30.5 millimeter. And the least relative roughness, which is 0.00005, thus result in the smallest coefficient friction value and contribute to the least head loss value. So factors contributing to error or inaccuracy in experiment data and the possible recommendation to improve the assessment result. So the error in the experiment it may due because parallax error when flow measurement was taken. Second, calculation error due to uncertainty and unstable flow rate, which has caused the reading height fluctuated in the manometer. So the recommendation to improve this is you can repeat experiment and compare and take the average value, and avoid parallax error by making sure the eye parallel to the meniscus when taking the reading. Okay, so that's all from me.
Last but not least, the conclusion can be made in this experiment are the major losses will calculate for two sections of the pipe with a different diameter. The smaller diameter pipe produces a higher friction factor across the section, which was caused by the higher ratio of the surface area of the inner pipe to the cross-sectional area. Thank you.